Hello everyone. Today, we, the group members of ME10, are here to present our project. The topic for this project is to study airflow behavior through different stages in a turbofan aircraft engine. The specimen engine that we are taking up for this project is Rolls-Royce Trent 800. As we know that Rolls-Royce is a leading manufacturing firm, Trent 800 is an example of their excellence. Trent 800 is widely used for Boeing 777 aircraft engine.
For this project, we used an Flow EFP for CFD simulation integrated with CAD. For the pre-processing part, we used a number of steps such as data procurement, where we collected turbofan geometry references and CAD models. For the geometry creation of the Trent 800 engine, we imported it into the Flow EFP. For defining contacts and interfaces, we ensured proper interaction between stationary and rotating components. We also set up the boundary conditions and meshing.
After pre-processing, we performed the main simulation. The simulation setup included solver selection, applying physical model like turbulence modeling, E omega SST model, defining flow properties like air density, viscosity, etc. Constraints were given velocity, running the solvers and converging the monitoring.
In post-processing, we analyzed the airflow patterns and extracted meaningful results. Like, we got the flow trajectories displaying the actual flow path of the air moving through the fan, compressor, and the turbine. Similarly, we got the results of the velocity distributions and the pressure distributions. Later, we got the flow contours in 2D and 3D displaying the flow of the velocity, temperature, and the pressure, and got our results in the form of converging graph. For our case setup, we defined air as a working fluid and used realistic materials like titanium and Inconel, defining the materials of our components. We defined the different rotating regions, like for the different stages in a turbofan engine, like defining rotating region for the fan, compressor, and the turbine with different respective RPMs, and set their inlet velocity and outlet pressure, and the turbulence model was selected. After the solver was converged, we moved to the post-processing, where we got the velocity and the pressure trajectories.
Coming on to the dynamic case setup, we have separated the entire rotation of this engine into three different zones. One being N1, which is at the main fan, giving rotation of 346 radian per second. Then at the compressor, we have given a rotating region of 733 radian per second. Moving on to the main turbine area, we have given a rotation of 1111 radian per second. We have given materials as per the real engine used materials of titanium and Inconel at various different regions of the engine. Moving on, once the solver is complete and the solution has converged, we can then plot the flow trajectories. We can plot flow trajectories from custom points which we can define from where we want the flow lines to emerge. Once they start to emerge, they follow the flow path as per the solution and the rotating regions that we have specified. We can see from the contours and refer them to the main graph, to the main scale, and then infer out the pressure values from the flow trajectories. Then we move on to the parameter specific cut plots. We have given cut plots for two values, basically for velocity as well as pressure. For velocity, we have given custom plots at the turbine section, fan section, as well as the compressor section. We can follow the contours, infer them from the main scale, and infer out the velocity values. Same goes for the pressure distribution. We have given a cut section view from the side middle profile of the entire engine. We can refer the contours to the scale and determine the pressure at various different areas. This was the entire analysis. We can then, from the flow trajectories as well as the specific cut plots, we can determine the velocity and the pressure values at various stages of the simulation of the engine, which was the main intent of our CFD analysis for this turbofan engine. Thank you.